And welcome back to the physics video lecture. This is Fluid Mechanics video lecture 9. So, we had gotten through to the wave equation. We're going to spend 1 hour talking about wave equation solutions and other interesting stuff. And I'll review what we had so far. So, to get to the wave equation, we had V is small. That allowed us to get rid of quadratic terms. We had pressure constant plus a small part here, and same for the density, constant plus rho prime. So those are the small fluctuations there. And we succeeded in finding that d squared density dt squared is equal to c squared del squared density, and the same thing for the pressure. And by the way, those are those little primed small density fluctuations, and d squared p dt squared was c squared del squared p prime. And our speed here, which is the speed of sound, we're talking about sound waves, c squared was equal to dp d rho, so the derivative of pressure with respect to density at constant entropy. So that's how far we had gotten. What we want to do is discuss the velocities and actually put pressure, density, velocity all in terms of the potential, the velocity potential. So I'll write here next, express in terms of phi, in terms of phi, for which we have first of all that the velocity is the gradient of phi, and from Bernoulli's equation we also have d phi dt plus p prime over rho naught equals 0. This is the Bernoulli's equation version for small velocities. Gets rid of the v squared term, right? So Bernoulli small v velocities. Okay. So yeah, what we want to do is have a wave equation for the velocity potential itself, because then we'll have everything in very compact form. So that's our next task. There are a couple of ways to do this, by the way. Let's just see. We're going to begin with dv dt equals minus 1 over rho naught gradient p prime. So again, this is Euler's equation for small velocities, which we're pointing out up there. Velocities are small. And d rho prime dt plus divergence of rho naught divergence of v is equal to 0. So these are, again, the Euler's and continuity equations under this assumption of small velocities, so forth, that we had last time. This time, we're going to do the following. We will use this expression here or actually we'll use the little derivation of this expression, namely, we're going to let P prime be equal to dP d rho constant S rho prime. Okay, that's a substitution we made before. We're expressing the pressure in terms of the density, and it's like the first term in a series expansion. And in this equation here, now for star, we get the d rho prime dt, we get 1 over dp d rho, which is a constant, d rho prime, so I'm sorry, d rho prime dt is equal to 1 over dp d rho dt prime dt. dp prime dt, and then plus rho 0 divergence of v is equal to 0. Now, the dp prime, we're going to use this. Okay, so we're going to make use of this equation and these two equations. We're going to take these two facts about velocity potential and plug them into here. I'll go up. Go up to here, so what do we have? 1 over dp d rho at constant s. dp prime dt is going to be minus rho naught d squared phi dt squared. So minus rho naught d squared phi dt squared. And then we're going to have plus rho naught divergence of v, but there's our del squared, right? Divergence of the gradient. So divergence gradient gives us del squared. So del squared v is equal to 0 using those guys. Okay. And this we have. When the dust settles on this thing, we'll have what we're looking for. So, let's see. I'll put it right here. The rho naughts cancel, minus sign gets rid of it when we bring one to the other side. And this is c squared. So yeah, we have d squared phi dt squared equals c squared del squared phi. So that's nice. That's what we were looking for. Now we can set all of these things up. Namely, we will set this equation up, and this equation up, and that's what we always work with when we're talking about these sound waves. And we can get the pressures and the densities via these derivatives here, right? So the pressure we can get, the densities we can get via this, and the velocities we can get via that right there. I think I'll put them all down in one place, and then we'll continue on. So let's see what we have now. So we have, what's the best order here? Well, yeah, we'll just say we've got our d squared phi t squared. Good, so we've got a wave equation for phi. We have c is the c squared is dp d rho at constant entropy. Now we also have this p prime is equal to dp d rho prime. That's just to give us the densities of the pressures. then we have v is equal to the gradient of phi. And finally, dp dt plus p prime over rho naught is equal to 0. Okay, so that relates all those quantities. Okay, so we're going to do a little bit of setting up solutions to the wave equation, just as much as we need, and then I'm going to do a kind of a list of topics that one could cover, but that we're not going to because we can't do everything. But we do have a few important points to make with all of this. Because at this point, you're just studying the theory of waves in general now. You've got a scalar wave equation, but the vector nature of what you're doing is also available. So let's see. Okay, so next, solutions to the wave equation. So we're looking for solutions phi of x plus or minus c times t. So any function of this form we can immediately see is a solution to the wave equation because we have two time derivatives brings out a c squared times two space derivatives. Okay. So immediately we have d squared phi dt squared, the two time derivatives, that's phi double prime of the argument times that plus minus c squared, which of course is c squared, to spatial derivatives, which is c squared d squared phi dx squared. Okay. So that's a traveling wave solution. And there's something else now that we can get out of this. It's that this is pretty important, so I'll even write here important. This wave is propagating in the positive or negative x direction, right? So phi of x and t equals, f of x plus minus ct propagates, it's a plane wave propagating in the plus or minus x direction. I'll just write in x, so there's our x-axis. Think of plane waves. And actually we're not quite at the plane wave aspect, it's more of a pulse at this point, or it could be a lot of things. But the main thing is it's propagating in x direction, and if we go back to here, v is the gradient of phi, we have vx equals d phi dx, and vy, d phi dy is 0, right? So from v equals gradient of phi, we have vx d phi dx, vy equals 0, vz equals 0. That means that we are looking at a longitudinal wave, okay? Because the velocity field is in the direction of propagation. Okay, yeah, or just say the vector is in the direction of propagation. So yeah, this tells us that we have a longitudinal wave, right? V is in the direction of propagation. V, direction of propagation. Yeah, I should point out, since we can generate these things out of the potential, of course, the velocity itself satisfies the wave equation. Right, because of this, I'll put this as a note here. And we could have discovered that without actually solving, or without going into the potential form here. We could have directly shown that the velocity as well as the pressure and density. So note V also satisfies the wave equation. And that's why this is, important derivation, that it turns out to be a longitudinal wave. So what's next? What's next is a list of things that one could do when studying waves, but that we won't actually do. Good, yeah, longitudinal wave right here, so important to actually rigorously demonstrate that. It's usually just claimed to be the case. It's certainly plausible, but this is the rigorous demonstration. Okay, so generally, we can prove and study reflection and refraction. Okay, so I'll just make a little list here. Law of reflection, to law of refraction, right? Snell's law, that can be shown directly with the wave formulation. Snell's law. Uppercase. We can study waves in a moving medium and then Doppler effects and stuff. So waves in a moving medium. And of course, waves being emitted from a moving source. Also a moving source. Right, Doppler effects. Waves in a bounded medium. Let's see what else I have on my list here. Yeah. And then you can have theories of musical instruments and things like that. So yeah, the whole study of waves, of course, is pretty enormous. One thing, though, that we made use of is group velocity. We already used the formula for group velocity. V group is, in fact, I can do it in a vector form, d omega dk, right? We did it for one variable, but it holds true this way as well. So there are a number of standard derivations of this formula, but I'm going to give a somewhat unusual derivation, but also a good one. So anyway, this is just to mention all the things that you can study when you have wave equations. These all hold true in fluids, and you would be talking about acoustics often. The waves in a gas or in a liquid. Okay, consult the clock. So what we're going to do next is just talk about traveling waves and monochromatic waves. And I hope to end with a proof of this. We'll see if we get there. Okay, so we've got our wave equation, and we want to start solving it a little more specifically than just this general expression up here. So next what we're going to consider is, let phi of x and t be equal to some, I'll just use the same letter, phi of x e to the minus I omega t. Or maybe I'll use f. F of x e to the minus I omega t. So we take this as our trial solution and go into the wave equation with it. So we get two time derivatives giving us minus I omega squared f of x e to the minus I omega t. And then we get c squared and two spatial derivatives, so that just gives us the f double prime of x e to the minus I omega t. So we've gone into the wave equation. Obviously these guys cancel, and we're going to get f double prime of x is equal to minus omega squared over c squared f of x, and that has as its solution, you know, an exponential here as well. So we can go ahead and say f of x is just equal to some constant e to the minus, or we can take plus e to the I omega over c times x. Okay. We'll just go ahead and go with this one. When we combine it with this e to the minus I omega t, we now have phi of x and t is equal to some constant e to the I omega over c x minus omega t. Okay, so far so good. So that has the form. We could also pull out the omega and cross multiply the c, but we'll leave that there for now. And I'll leave all these things up here. They could be useful. Okay, so continuing, what do we have here? We have phi of x and t equals a e to the I. Now I'm just going to define omega over c is equal to k minus omega t, where k is equal to omega over c. And and because of the sinusoidal or the periodic nature of the exponential, or sine and cosine complex exponential, we have k is also equal to 2 pi divided by lambda, because that's how long it takes to repeat this, right? K times lambda, 2 pi when you've done a full wavelength. So good, we have that. And we want to next generalize this to 3 dimensions. Okay, so this traveling wave solution, this traveling monochromatic wave solution can be generalized to 3 dimensions. Generalize to 3 dimensions, then we're going to have phi of r and t equal to a e to the I vector k dot r minus omega t. And now k is going to be the direction of propagation, where I'll go ahead and define an n unit vector k over magnitude k gives us the direction of propagation. And this is all completely consistent and easy to see, because if we go back into our wave equation with the del squared, first of all, the time derivatives are still going to bring out just minus omega squared, right? Time derivatives not going to be any change. The 3 spatial derivatives, c squared times those, are going to give k sub x squared plus k sub y squared plus k sub z squared, which is k squared. So yeah, make sure you see this. So check this, make sure you agree that that's what's going on. Okay, the whole direction property is very nice as well. So if k is pointing in a certain direction, all of the r's that are perpendicular to that k will give you the same phase, and that's how you'll get plane wave fronts propagating in the k direction as opposed to just in the positive x direction. Okay, via the property of this dot product k dot r. Good, so this is important plane wave solution, monochromatic plane wave in the direction of propagation, which is just given by the vector k itself. So let's write that down. Traveling monochromatic plane wave in direction k. Same direction as k. Now if you turn it into a unit vector like that, then it's the direction of n there. And if you do that substitution, you'll even see, substitute k like this, you'd have k times that n direction there. Okay, so n hat dot r. So that'll work out. Also, we have, since we've gone to the vectors here, we now have, I'll just put this as a note as well, we're going to use it. So this omega squared over c squared equals k squared. Omega squared over c squared equals k squared. That's from up here in the 3 dimensions. That's k sub x squared plus k sub y squared plus k sub z squared. And since we're going to use this, I'm going to go ahead and write it out. So you could also say omega is equal to c square root of kx squared plus ky squared plus k z squared, like that. Okay, let's consult the clock again. Perfect. focusing on this thing, you know, we have A is a constant, the vector K is a constant, omega is a constant, and all these relations are up here as well. So we'll focus on this. I need the whole board. And I'm going to do a split board here. I think that's the best way to talk about. So what we want to do is visualize and get a feel for what's going on here. We'll just do it one-dimensional drawing, similar to what I had before. And then we're going to look at the situation. What happens if A is not a constant? What happens if K is not a constant? Okay. So that would be a more general solution to the wave equation. So let's see how we can pull this off here. Split the board. Rewrite this thing up here. We've got our phi of R and T, A, e to the I, K dot R minus omega T. And we're saying A is constant. K is constant. And C is constant. But remember, the C, the speed of sound, depended on the derivative of the pressure with respect to the density, and pressure and density don't have to be constant throughout the medium. In fact, they're not constant in a sound wave, but those are really tiny fluctuations against the, you know, the general constant expression. So, if we have a direction, then I'll just go ahead and call this is the direction K, you know, this is our N unit vector. That's the direction of propagation. Then the surfaces of constant phase for some fixed time, K dot R, surfaces of constant phase are separated, say, by lambda here, okay, and they're propagating in the positive N direction. That's what we're looking at here. So for example, if we called this the origin, then K dot R would of course be equal to 0, okay? But then if we take our R's, and these R's would be perpendicular, then if we take the R's here, we're going to get that dot product coming around to a constant, and then we go out to here, this surface, all the K dot R in these surfaces will be constants, right? Progressively larger constants. So those are surfaces of constant phase. And they're propagating, like I said, to the right here, separated by wavelength lambda. So this was for constant C. Now the question is, what if we have a little inhomogeneity in this whole system so that the speed of sound is not constant? Okay. If we go into this differential equation with a non-constant speed of sound, things are going to be a lot different. And the solution is going to be much more difficult. So this was for that situation. So what I'm going to say is next here, suppose C is not constant. The speed of sound is not a constant. We still have our wave equation. Our solutions are going to have to look like this. In other words, the amplitude and the direction are no longer going to be constant. So suddenly we're looking at an amplitude, I'll use lowercase a of r and t, and I have e to the I times c of r and t, right? I no longer have this constant k, this expression, no longer have a constant amplitude. So if I go into the wave equation with this, I'm going to get a very complicated set of equations. What I can do, though, is consider the short wavelength limit. So the short wavelength, or the short wavelength case. And I'll do a picture to visualize what's going on. See, we're no longer going to have propagation in a straight line if the speed of sound changes appreciably. We already know that from Snell's law, right? If the speed of sound changes abruptly, it's just like Snell's law in optics, by the way. The speed of sound changes abruptly from one medium to another, then the direction of the ray changes. So if we had a gradient in the speed of sound, we can expect the ray to change direction gradually. So here's what I'm going to draw. Imagine we have a ray that's coming here, but because we have changing speed of sound, our wave fronts are gradually, right, they're still perpendicular to the changing wave number, okay, or changing wave vector. The short wavelength case is saying that these wavelengths here are very small with respect to the dimensions over which the direction changes appreciably. Okay. So I'll put that in words. Lambda is much less than the dimension or length scale over which the direction changes appreciably. Length scale over which the direction changes appreciably. And we're also going to require that this is also going to change very slowly with respect to this lambda as well. Also, lambda much less than change of amplitude A. By which we mean the regions over which the amplitude changes. Okay. So that constitutes the short wavelength approximation. And what we can do now, let's see what we got to get rid of here. Well, that's about as clear as you can make the case, right? What we can do then is expand this expression up here in a little Taylor expansion. Guess I'll erase all these now. Okay, so we're working with these assumptions. Okay, the short wavelength case. Okay, everything's up there. What we're going to do is choose an arbitrary origin. An arbitrary origin somewhere there. expand C and by the way, this thing is called the Eigenal, so I should have put that down there. Eikonal. That's what this thing is called. So we just expand it in a Taylor series. So we'll start with a constant, and then since it's a function of R and T, we could say we have plus gradient C dotted into R plus deep C dt times T. And this is for very small R and T. Okay. So what we do is compare this now to this equation up here. And so I'll write and compare. So we compare. We have e to the I k dot r minus omega t versus e to the I, right? The e to the I constant just pulls out, just absorbs into the constant there. E to the I gradient c dot r plus d omega t. Oops, that's a little fast. Plus d c dt times t. So we're comparing these, and what we see is that we can identify k with the gradient of c, and we can identify omega with minus deep c dt. So then we have gradient c, it's k locally, but now this is something that can change in space, right? And dc dt is equal to minus omega. So since we had k squared equals omega squared over c squared for this left side, for the right side we obtain del c squared equals 1 over c squared deep c dt squared. And if there's no explicit time dependence, we can do even better here. We have, or k squared equals omega squared, let me write this one out. Or kx squared plus ky squared plus kz squared on the one hand, and over here we'll have deep c dx squared plus deep c dy deep c dz squared equals, gotta erase something here. And I'm just going to look at the case where C does not have explicit time dependence. So if there's no explicit time dependence, then we can just go back to calling this omega squared over c squared. The difference is that this c is a function of position. It is no longer constant, right? That should be written somewhere. This is no longer a constant, so this is a function of position. And this is a differential equation. It's called the Eigenal Equation. Let's get that in blue. Eigenal Equation case when deep C dt is constant. Did I say, I made a mistake there about the not explicitly dependent on time. It's equal to constant equals omega. So we still have our monochromatic waves, but we no longer have a constant speed of sound, and therefore they can move. And this is the Eigenal equation. So how much time do I have now? Okay, we have just enough time to bring this to a good conclusion. So yeah, what do we do with this? The last development I'm going to do here, this is after all the short wavelength limit of a general wave theory, so this has a lot of application. It turns out that there's a very close relation between this Eigenal equation and classical mechanics. Okay. So that's what I want to draw out in my last couple of boards here. Okay, I think we have, yeah, so again, this is a differential equation for this unknown quantity C, whose meaning is that the gradient of this gives the direction of the waves, of the wave, the gradient of this is perpendicular to the wave fronts, and it can change as opposed to just being constant, because this is a function of position. Good, so let's send this up. Got our Eigenal equation. Good, here we go. I'm going to split the boards again. So there's going to be a relation here between classical mechanics and what we've just discovered. That's what I'm going to tease out. So over on this side, Eigenal equation. So I'm going to go ahead and write it in this order. So here we would have deep C dt is equal to minus omega. And then we'll have the gradient of C is k locally, and then we have gradient of C squared equals omega squared over C squared, and in parentheses I'll point out this, the idea here is that this is a function of position. Okay. So classical mechanics. Here, these are the equations in classical mechanics that are related to this. You have ds dt is equal to minus h, where S is the action, h is the Hamiltonian, is the energy. Then you have the gradient of S is equal to P And here you have, I'm just going to write the gradient of S squared is equal to 2m e minus u, and in parentheses, that is a function of position. Okay. Now this you may not recognize yet, so I'll put this as a note. P squared over 2m plus u, say of r, is equal to h. Right? This would be your one particle Hamiltonian, right? P squared over 2m plus u of r equals h, and this has just been rewritten. Bring the h over, bring the u over to multiply by 2m, okay, and then make that substitution, gradient S is equal to P. So yeah, this is just the classical Hamiltonian. This appears from Hamilton-Jacobi theory. So I have to write Hamilton-Jacobi theory. But Hamiltonians may be more familiar. So over here, if we go down into Hamiltonian mechanics, because this is the Hamiltonian, we know that we have P dot, so I'll just write Hamilton mechanics. We have P dot is minus dH dr, okay, and R dot is equal to dH dP. These are gradients if you want, right? 3 equations at a time, single point particle. So there is a complete analogy between these systems here and the classical mechanics here. So if we take it at this level, we get, what do we get for P dot? We get K dot is equal to d omega dr, and we get R dot is equal to d omega dk. And this just happens to be the group velocity. So if you accept this analogy here, then we've demonstrated our expression for the group velocity. There are other ways to get this expression, but this is kind of interesting, right? These analogies can actually be extended. You end up with a principle of least action on this side, and you end up with Fermat's principle on this side. So, but what's interesting is that you can use the formal methods of classical mechanics to solve the Eigenal Equation and of optics and acoustics. So for us, because we're talking about waves in fluid, we're actually talking about acoustics, geometrical acoustics. So yeah, this whole subject would be called geometrical acoustics. But formally, it could be the same as geometrical optics. So I can wrap it up just by giving this example. Name of the one that's up on the board there. So to get a non-constant K, you'd have to have an omega that's explicitly dependent on R. And that would give you the change of the wave vector. But I will do this group velocity for equals c root kx squared plus ky squared plus kz squared. So that's our original constant speed, constant omega, but this is omega of k. We have v group is equal to d omega dk, but this is basically the gradient with respect to this vector k. So this is a very well-known calculation. It's just k vector over k. So what do we have? The group velocity is the constant speed of sound in the direction of the wave vector. So that comes right out of this definition here. Group velocity, v group right there. Okay, good. That more or less will wrap it up. That was this one. So we can also note, I just said it, but I'll just go ahead and write this under there. Note for d omega dr equals 0, we have k dot equals 0. That means k equals constant. If there is R dependence in there, because the speed of sound changes, then you're going to get k not being constant. Now the trivial, well not the trivial, but the one case of this that we're very familiar with, so I'll add this as a final note, C is not equal to constant. If we were spending more time just on the wave aspect, we would actually prove the Snell's law. So I'm going to write this Snell's law, and you know, you guys remember you've got N1, N2, angle incidence, theta incident, theta refracted. And in this case, N2 is greater than N1. But because of the relation between the speed of sound and the index of refraction, similar to the speed of light and the index of refraction, if we had C1, so over here we would have here N1 is less than N2. If this were C1 and C2, the speed of sound was above and below this demarcation. Here, C1 is greater than C2. And remember, I don't want to confuse this too much. Snell's law for light, the speed, yeah, just don't confuse this. This is, of course, not the speed of light. This is the speed of sound in our medium here. So over here, we have generally N is equal to speed of light over speed of light. No, speed of light in the vacuum over the speed of light in the medium. And here it's just the speed in the medium. Okay. Good. So yeah, the point was when the speed of sound changes, the direction of k changes as well. Okay. And this is the more general version of that. Good, we'll leave it right there. That's actually quite a bit of ground, but this Eigenal equation, this whole Eigenal theory, it plays a really big role even today in physics because it's the short wavelength limit. If you're doing the difference between classical and quantum mechanics, it's the going towards the classical limit, but not yet classical. If you're doing optics, you have it as well. If you're doing acoustics, you have it as well. Okay, we'll leave it at that and pick up with next time I want to start talking about fluid flows, Euler equation with viscosity. So we're finally going to get there. This was an important detour just to show the richness of the whole theory. Good, see you guys next time.